All right, we're looking at the root test today. This is our second to last test. We use it to determine, of course, congruence and divergence, and it's especially well suited for when we have a series that involves something to the nth power. So, um, one thing that we know about the root test is that it's for the sum of some series, a sub n, that where if we take the limit as n approaches infinity of the nth root of the absolute value of a sub n, if it is less than 1, then the series converges absolutely. So this is basically like if the inside part of the root is a fraction, then we know that when we take the square root or the nth root, it's going to make our series is just going to is going to diver or converge because it's going to get very, very small very quickly. Okay. What we also know is that if that same limit is greater than 1, then it's going to diverge, and if the series or if the limit is equal to 1, then it's inconclusive. Okay, so three conditions, um, or three outcomes. One thing we know as well is that sometimes we end up with this limit, the limit as n goes to infinity of n to the 1 over n, and I'm going to tell you that equals 1. Okay. Um, I'll do a separate video of the proof of that. Okay, so I'm going to use the root test to determine convergence. So we're going to start with, I notice that I'm raising my e to the n and my n to the n, so I am going to use the root test here. I'm going to use the limit as n approaches infinity of the nth root of the absolute value of e to the 2n over n to the n. And that will basically cancel out my powers of n. So the limit as n approaches infinity of e to the 2 over n, because what's this and this and this are going to cancel. So now I have e to the 2 over infinity, which is going to give me 0, which is less than 1. So the series converges absolutely. We can just say the series converges by the root test. Okay, next. The sum from n equals 1 of negative 3n over 2n plus 1 to the n. So again, we're raising to the n power, so I am going to try the root test. So as n goes to infinity of the nth root of the absolute value of negative 3n, I'm going to do big parentheses, negative 3n over 2n plus 1 to the n power. Okay. And what the absolute value will do is make the inside part positive. So I'm going to write 3n to the n over 2n plus 1 to the n, and the n will cancel because of the root. So the limit as n approaches infinity of 3n over 2n plus 1, this is the numerator and the denominator grow at an almost equal rate. So we go ahead and divide the leading terms. And I get 3 over 2, which is greater than 1. So the series diverges by root test. Okay, the next one. The sum as n equals 1 to infinity of n over to the n. So I'm going to start the limit as n approaches infinity of the nth root of n over 2 to the n. So I am going to just rewrite this. This is the limit as n approaches infinity of n over 2 to the n. I'm going to use a rational exponent of 1 over the n. Okay, so I end up with, I'm going to apply the power to both bases. So I have n to the 1 over n over 2. And then what happens here is that the limit, remember our fact? I remember. The limit as n approaches infinity of n to the 1 over n is equal to 1. So the limit of the top is equal to 1. And then the limit of the denominator is just 2, just 1/2. So we're, 1/2 is less than 1, so the series converges by root test. Okay. All right. So the sum from n equals 1 to infinity of n factorial to the n over n to the n to the 2. Okay. So lots of to the n, so I'm just going to go ahead and try and use the root test. And also this is called the root test section. Okay. So I have the nth root of n factorial raised to the n over, I'm going to apply the power to a power rule, so n to the 2n, and the powers of n will cancel to give me the limit as n approaches infinity of n factorial. Oh, I needed to put the absolute value here. Okay, n factorial over n squared, and n factorial rises way faster. So this limit is going to go, well, way faster than n squared because that's a quadratic. So this limit is going to go towards infinity, which is greater than 1. So the series diverges by root test. Okay, that one's fun.